Tonight, we're diving into one of astronomy's strangest measurements, a unit of distance called the parsec that hardly any star actually occupies. Yet it dominates every professional astronomical paper written today. By the time we're finished, you'll grasp not only what a parsec means, but why a measurement technique from 1838 still controls how we describe the universe. If these deep dives resonate with you, consider leaving a like or subscribing. Let's get started. Picture yourself as an astronomer in the year 1837. Every night, you position yourself at your telescope, staring into darkness at a faint point of light known as 61 Cygni. You're aware that Earth is hurtling through space, completing its orbit around the Sun at incredible velocity. You understand that with enough patience, enough precision, enough dedication, you might catch that star's position shifting minutely against the backdrop of more distant stars. And if you can capture that shift, measure it accurately, you'll achieve something humanity has pursued for 2 millennia. You'll determine how far away a star truly is. Friedrich Wilhelm Bessel accomplished precisely this. What he couldn't have anticipated was that his measurement would establish a distance unit still dominating astronomy almost 200 years later. A unit that feels completely counterintuitive to anyone outside the discipline. A unit that marks no natural cosmic threshold. A unit founded entirely on the geometry of his measurement approach, the parsec. For the vast majority of human existence, stellar distances remained completely unknown. The ancient Greek astronomer Hipparchus, working around 130 BCE, catalogued more than 1,000 stars. He meticulously measured their positions, monitored their movements through the sky, documented their apparent brightness. But their distance? He possessed no method to determine it. His best hypothesis placed them on a crystalline sphere situated beyond the planets, all equidistant from Earth. This wasn't ignorance or failure of creativity. It represented the most reasonable explanation matching the observations available at the time. The stars seemed to be fixed luminous points that never shifted positions relative to one another. They maintained perfect arrangement night after night, year after year, century upon century. The ancient Greeks actually coined a specific term for this celestial sphere. They named it the firmament, derived from Latin meaning to make firm or to solidify. The concept held that stars were literally embedded within a solid crystalline sphere rotating around Earth once every 24 hours. This sphere existed beyond the planets, which the Greeks recognized moved against the stellar backdrop. They had carefully tracked Mars, Jupiter and Saturn, watching these wandering celestial objects trace intricate trajectories through the constellations. But the stars themselves never moved relative to each other. Aristotle, writing during the 4th century BCE, argued this celestial sphere must consist of a fifth element, something distinct from the Earth, water, air and fire found beneath the Moon's orbit. He termed it ether or quintessence. This substance was supposedly perfect, unchanging, eternal. The stars embedded within this sphere shared its perfection. They never varied in brightness, never materialized or vanished, never moved except in their daily rotation with the sphere itself. This model persisted for 2,000 years because nobody possessed instruments sensitive enough to detect stellar parallax or proper motion. The stars genuinely appeared absolutely motionless. Every observation validated the model. When Ptolemy assembled his comprehensive star catalogue around 150 CE, documenting over 1,000 stars and their precise positions, he discovered the identical patterns Hipparchus had recorded 3 centuries earlier. The constellations hadn't altered their configuration at all. For 2 millennia, nobody improved upon this understanding. The necessary technology simply didn't exist. Telescopes were finally invented during the 1600s, revealing extraordinary details about the Moon, planets and stars. Galileo observed mountains on the lunar surface and 4 moons orbiting Jupiter. He determined that the Milky Way comprised countless individual stars, Yet he still couldn't answer the fundamental question of distance. The star still appeared completely fixed in place. If something doesn't exhibit motion, you cannot triangulate its distance. You need to observe an object from two distinct positions and measure how its apparent position shifts. That's exactly how your brain perceives depth. Your two eyes capture slightly different perspectives of the world, and your brain exploits that difference to gauge distance. Close one eye and attempt to touch something. It becomes more difficult because you've eliminated that depth perception. Your brain requires the parallax between your eyes. For stars, we needed something comparable, but on a cosmic magnitude. Human eyes are separated by merely about 6 centimeters. That's sufficient to provide depth perception for objects several meters away, but completely inadequate for anything at astronomical distances. We needed a vastly larger baseline. By the 1600s, scientists had developed an ingenious idea. Utilize Earth's orbit around the Sun as your triangulation baseline. Johannes Kepler had established that Earth orbits the Sun in an approximately circular trajectory. By the mid-1600s, astronomers had measured Earth's orbital dimensions fairly precisely by observing transits of Venus across the Sun's disk. They understood Earth orbits in a path roughly 300 million kilometers in diameter. That's 186 million miles. This means in January, Earth occupies one side of the Sun, and 6 months afterward, in July, Earth sits on the completely opposite side. Observe a star in January, record its precise position against the background of more distant stars, then observe that identical star in July from the opposite side of the orbit. You're viewing from two positions separated by that entire diameter. It's equivalent to having eyes separated by 300 million kilometers instead of 6 centimeters. Even the closest stars should display a minuscule shift against the more distant background stars. This shift is called stellar parallax. Measure this shift, apply basic trigonometry, and you can calculate the distance. The concept is elegantly straightforward. Draw a triangle. The base represents Earth's orbital diameter. The apex is the star. Measure the angle at the star and you can determine how distant it is. Simple geometry that any student learns in school. The execution, however, proved nearly impossible. The difficulty was that the shift is incredibly minute. We're discussing angles smaller than 1 arcsecond. To comprehend how tiny 1 arcsecond is, imagine dividing a degree into 60 parts. Each part constitutes 1 arc minute. Now divide each arc minute into 60 additional parts. Each of those is 1 arcsecond. So 1 arcsecond equals 1/3600th of a degree. To provide you a physical sense of this, if you hold a tennis ball at a distance of 1 kilometer, the ball appears approximately 1 arcsecond wide. If you're standing on a beach and observe a ship on the horizon 10 kilometers distant, a person standing on that ship's deck appears roughly 1 arcsecond tall. That's the kind of precision 17th century telescopes would require to detect stellar parallax. They couldn't accomplish it. The finest telescopes of that era had mechanical vibrations larger than the signal astronomers were attempting to detect. Atmospheric turbulence blurred images by several arcseconds. Temperature fluctuations made telescope components expand and contract by amounts that disrupted alignment. Even the astronomer's own heartbeat could introduce vibration substantial enough to ruin measurements. The foundations of observatory buildings settled and shifted with temperature variations. Wind pushed against telescope tubes. Robert Hooke attempted it in 1669. He was a brilliant scientist, one of England's premier experimentalists. Hooke had contributed to optics, mechanics, astronomy and biology. He coined the term cell after observing the structure of cork under a microscope. He formulated Hooke's law of elasticity. He was a serious scientist addressing a serious challenge. Hooke constructed a special telescope mounted within a tall building to minimize atmospheric distortion. The reasoning was that mounting the telescope at elevation would position it above some of the turbulent air near ground level. He observed a bright star called Gamma Draconis for months, took meticulous measurements, detected what he believed was a shift in position. He published his findings, claiming to have measured stellar parallax. He was mistaken. What Hooke had actually detected was likely a combination of instrumental drift and observational error. The shift he measured was too large to be genuine parallax, and inconsistent with what we now know about Gamma Draconis's actual distance. James Bradley tried in 1725. Bradley was Astronomer Royal of England, one of the most respected observational astronomers of his generation. He built careful instruments, developed rigorous measurement techniques, and observed systematically. Bradley did detect something remarkable, an apparent yearly motion of stars in small ellipses. But it wasn't parallax. What Bradley had discovered was stellar aberration, an optical effect caused by Earth's motion through space, combined with the finite speed of light. Imagine running through rain, even if the rain is falling straight down. From your perspective, it appears to come at an angle because you're moving through it. Light from stars behaves similarly. Earth's motion makes starlight appear to come from a slightly different direction, depending on Earth's velocity at that moment. This was an extraordinary discovery. It proved Earth was moving, which supported the Copernican model. It also provided the first solid evidence that light travels at finite speed. But it wasn't parallax. It didn't reveal stellar distances. The effect was too large, about 20 arc-seconds, and showed the wrong pattern. True parallax creates shifts that reach maximum when Earth is perpendicular to the star's direction. Aberration reaches maximum when Earth moves directly toward or away from the star's direction. William Herschel tried in the late 1700s. Herschel was the most accomplished observational astronomer of his era. He had discovered Uranus in 1781, the first planet discovered in recorded history. He had built the largest telescopes in the world. He had systematically surveyed the sky, cataloguing thousands of double stars and nebulae. If anyone could detect parallax, it should have been Herschel. He tried for decades using his finest instruments. He developed a clever method. He would observe pairs of stars that appeared close together on the sky. He assumed one was nearby and one was distant. The nearby one should show parallax while the distant one remained fixed, creating a measurable relative shift. Ingenious approach. But even with this method, Herschel couldn't detect parallax. The shifts were simply too small for his instruments to resolve reliably. By 1830, detecting stellar parallax had become astronomy's greatest unsolved challenge. The theoretical framework existed. The observational strategy was clear, but nobody could execute the measurement with sufficient precision. Then, almost simultaneously, 3 astronomers succeeded within a few years of each other using different stars and slightly different techniques. Friedrich Wilhelm Bessel in Germany focused on 61 Cygni, a faint double star in the constellation Cygnus. He chose it specifically because it had large proper motion across the sky, suggesting it might be relatively close. He used a heliometer, a specialized telescope with a split objective lens that could measure tiny angular separations very precisely. Bessel observed systematically throughout 1838, measuring 61 Cygni's position relative to several reference stars visible in the same field of view. By the end of the year, he had detected a clear parallax shift. He measured it at approximately 0.314 arc-seconds. Thomas Henderson in South Africa focused on Alpha Centauri, the bright star system visible from southern latitudes. He made his observations earlier than Bessel, actually during 1832 and 1833, while serving as director of the Royal Observatory at the Cape of Good Hope. But Henderson was cautious about his results. He doubted his measurements. He returned to England and spent years reanalyzing his data, before publishing in 1839. By then, Bessel had already announced his results for 61 Cygni. Henderson measured Alpha Centauri's parallax at about 1.16 arc-seconds, making it even closer than 61 Cygni. Friedrich Wilhelm Struve in Russia focused on Vega, one of the brightest stars in the northern sky. Struve used the Large Refractor Telescope at Dorpat Observatory, one of the finest telescopes available anywhere. He published his results in 1840, measuring Vega's parallax at approximately 0.26 arcseconds. All three measurements were correct. All three astronomers had finally succeeded where everyone before them had failed for 2,000 years. They had measured the distances to stars, but there was a problem. How do you report these distances in meaningful terms? The numbers were enormous by any terrestrial standard. Bessel's measurement of 61 Cygni's parallax at 0.314 arcseconds corresponds to a distance of about 100 trillion kilometres. That's 100 followed by 12 zeros, or about 10 light years the distance light travels in 10 years. But light years weren't in common use yet. Astronomers hadn't standardised on any particular distance unit for interstellar space. They had astronomical units for measuring distances within the solar system, but nothing established for stars. One option would have been to simply report parallax angles directly. Just say 61 Cygni has a parallax of 0.314 arcseconds. This has the advantage of being a direct measurement. It's what you actually observe, but it has a serious disadvantage. Smaller parallax numbers mean larger distances. It's inverted. A star with parallax of 0.5 arcseconds is twice as close as a star with parallax of 0.25 arcseconds. This is mathematically correct, but psychologically backwards. We intuitively want larger numbers to mean larger distances. Another option would be to calculate distance in meters or kilometers. But the numbers become absurd. Saying 61 Cygni is 100 trillion kilometers away doesn't convey much intuition. The number is too big to comprehend. Your brain can't grasp the difference between 100 trillion and 200 trillion in any meaningful way. A third option emerged from the geometry of the measurement itself. Define a distance unit based directly on parallax. Specifically, define the distance at which a star would show exactly 1 arcsecond of parallax. This turned out to be remarkably useful for working astronomers. If a star shows 1 arcsecond of parallax, it sits at 1 parsec. If a star shows half an arcsecond, it's at 2 parsecs. If it shows 1/10 of an arcsecond, it's at 10 parsecs. The conversion is immediate and intuitive for anyone working with parallax measurements. This is how the parsec was born. Not from any natural cosmic boundary or physical principle, but purely from the convenience of the measurement technique. The word parsec itself is a contraction, parallax of 1 arcsecond. It's a manufactured term describing a manufactured unit defined by human measurement conventions. Here's what makes it strange. 1 arcsecond is completely arbitrary. There's nothing special about dividing a circle into 360 degrees. Ancient Babylonians chose that number around 2000 BCE because it has many divisors, making calculations easier. 60 divides evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20 and 30. That's convenient for arithmetic, but it's arbitrary. We could have divided circles into 400 degrees or 1000 degrees or any other number. Different cultures did exactly that. The French briefly tried decimal degrees during the French Revolution, dividing circles into 400 grads. If we had chosen 400 degrees for a full circle instead of 360, an arcsecond would be a different size. A parsec would correspond to a different distance. The entire unit is founded on an arbitrary human choice about angular measurement that has nothing to do with cosmic structure or physical law. Compare this to other fundamental units. A meter was originally defined as 1/10,000,000th of the distance from Earth's equator to the North Pole. That's at least based on Earth's physical size. A kilogram was defined as the mass of 1 litre of water, again connected to a physical property. A second was defined as a specific fraction of Earth's rotation period, 1/86,400th of a day. These units have some connection to physical reality, even if the connections are somewhat arbitrary. The parsec has no such connection. It's based entirely on the measurement technique used to determine it. It's as if we defined a unit of mass called the balance gram as the mass that makes a specific type of balance scale tip exactly 1 degree when placed on one side. That would be absurd. Yet that's essentially what the parsec does for distance. Despite this strangeness, the parsec caught on. Why? Because it was genuinely useful for working astronomers. When you're measuring parallaxes all day, having a unit that converts directly from your measurements is incredibly convenient. You measure a parallax of 0.5 arc seconds, you immediately know the distance is 2 parsecs. No calculation required, no conversion factors to remember. The unit embeds the measurement technique directly into the distance scale. This matters more than you might think. Scientists don't work in abstract theoretical spaces. They work with instruments that produce specific types of measurements. They work with data tables filled with numbers. They work with calculations they need to perform repeatedly. A unit that streamlines that workflow has enormous practical value, even if it seems bizarre to outsiders. Think about how a carpenter works. They don't measure lumber in meters and convert to feet. They don't measure in centimeters and convert to inches. They use the units their measuring tools display directly. A carpenter in America uses inches and feet because their tape measure shows inches and feet. A carpenter in Europe uses centimeters and meters because their tape measure shows centimeters and meters. Using the units your instruments produce directly is simply more efficient. For astronomers measuring parallaxes, their instrument produces arc-second measurements. Having a distance unit that converts directly from arc-seconds is like having a tape measure that shows the units you actually care about. You eliminate a conversion step. You reduce opportunities for arithmetic errors. You make the workflow smoother. But there's another factor at play here, something more subtle and more powerful. Once a measurement unit gets established in a scientific field, it becomes entrenched through network effects. Every paper uses it. Every database stores distances in those units. Every student learns it. Every textbook teaches it. Changing becomes incredibly difficult because you'd need to coordinate across thousands of researchers, institutions, and publications simultaneously. This is exactly what happened with the parsec. By the late 1800s, parallax measurements were becoming routine. More observatories were measuring more stars. Distance catalogues were being compiled. The parsec was convenient for this work, so it got used. As more data accumulated in parsecs, it became harder to justify using anything else. You'd have to convert all existing data. You'd have to retrain all working astronomers. You'd have to rewrite all the textbooks. The costs of switching mount rapidly, while the benefits remain unclear. Consider what happened with the light year, which actually seems more intuitive to most people. A light year is the distance light travels in 1 year. That's conceptually straightforward. Light moves at 300,000 kilometers per second. In 1 year, it covers about 9.46 trillion kilometers. That's 1 light year. Simple enough. For popular science communication, light years work beautifully. Saying Alpha Centauri is about 4 light years away immediately conveys something meaningful. Light from that star takes 4 years to reach us. If we could somehow travel at light speed, we'd need 4 years to get there. The unit carries intuitive meaning, but for working astronomers, light years have disadvantages. The conversion from parallax to light years requires arithmetic. You measure a parallax, you need to calculate distance in parsecs first, then convert to light years if desired. That's an extra step. More importantly, many astronomical calculations work more naturally in parsecs than light years because of how certain equations are structured. For example, calculating absolute magnitude from apparent magnitude and distance uses a formula that's cleaner with parsecs. Absolute magnitude is how bright a star would appear at a standard distance. Apparent magnitude is how bright it actually appears from Earth. The relationship involves distance, and the formula works elegantly when distance is in parsecs, because the standard reference distance is defined as 10 parsecs. If you use light years instead, you need conversion factors cluttering up the equation. it becomes messier. Parsecs keep the equations clean. This might seem like a minor convenience, but when you're doing these calculations repeatedly, day after day, paper after paper, the difference matters. The same pattern appears in many other astronomical calculations. Stellar luminosity equations work cleanly in parsecs. Galactic distance scales use parsecs naturally. Mass calculations for binary stars work better with parsecs. It's not that you can't do these calculations in light years, you absolutely can, but you'd need extra conversion factors scattered throughout your equations. The math becomes more cumbersome, so professional astronomers stuck with parsecs while popular science communication gravitates toward light years. This creates an odd situation where the public hears about light years, but professional literature uses parsecs almost exclusively. If you read a NASA press release about a distant galaxy, it'll probably mention light years. If you read the actual research paper that press release is based on, it'll use parsecs or kiloparsecs for distances. This division actually serves a useful purpose. It allows technical communication to use units optimized for technical work, while public communication uses units optimized for intuitive understanding. Both groups get what they need. The cost is that there's a translation barrier between professional and popular astronomy writing. But here's where it gets really interesting. As astronomy expanded beyond measuring nearby stars, the parsecs scaled in predictable ways. For more distant objects, astronomers use kiloparsecs, 1,000 parsecs. For really distant objects, they use megaparsecs, 1 million parsecs. For the most distant objects we can observe, they use gigaparsecs, 1 billion parsecs. These scaled versions maintain the same advantages as the original parsec. A galaxy 10 kiloparsecs away is 10,000 parsecs away. The conversion is trivial. More importantly, many astronomical phenomena have characteristic scales that fall naturally into these ranges. The Milky Way's disk is about 30 kiloparsecs in diameter. Nearby galaxies are typically measured in megaparsecs. The scale of the observable universe is measured in gigaparsecs. Using these scaled units means the numbers stay manageable. Instead of saying the Andromeda galaxy is 778,000 parsecs away, we say it's 778 kiloparsecs away. Instead of saying a distant quasar is 4,000 parsecs away, we say it's 4 gigaparsecs away. The numbers stay in ranges humans can actually work with mentally. Compare this to what would happen if we insisted on using meters for everything. The nearest star would be at about 40 trillion meters. That's a number so large it conveys nothing. Your brain can't process it. Even writing it requires scientific notation, but saying Alpha Centauri is 1.3 parsecs away gives you a number you can actually think about and compare to other stellar distances. This scaling property is genuinely useful. It's one reason the parsec has persisted despite its arbitrary origins. The unit happens to be roughly the right size that its 1,000-fold and million-fold multiples correspond to meaningful astronomical scales. That's partly coincidence, and partly the fact that the parallax measurement technique naturally probes distance scales where parsecs are appropriate. You might wonder why astronomers didn't just adopt light years and create kilo light years, mega light years, and giga light years. They could have. Some people even use these terms occasionally, but by the time such scaled units would have been useful, parsecs were already entrenched. The scientific literature was already using parsecs. The databases were already storing parsecs. The community had already converged on parsecs as standard. Switching at that point would have required enormous coordination costs for unclear benefits. Sure, light years might be slightly more intuitive for public communication, but that's not enough to justify rewriting decades of scientific literature, converting all existing databases, and retraining an entire scientific community. The inertia of established practice is powerful. This reveals something important about how science actually works. Scientific progress isn't just about discovering new facts or developing better theories. It's also about building infrastructure, establishing standards, and creating shared practices that allow researchers to communicate efficiently. Once that infrastructure exists, it becomes sticky. Changing requires overcoming not just technical barriers, but social and institutional ones. The parsec is a perfect example. It's not the best possible distance unit by any objective measure. It's based on arbitrary angular conventions. It marks no natural cosmic boundary. A better unit would probably be based on something more fundamental, perhaps the speed of light, and time, giving us something like the light year but optimized for astronomical calculations. But science doesn't always use the best possible tools. It uses tools that are good enough and already established. The parsec is good enough. It works for the calculations astronomers need to do. It's familiar to everyone in the field. The costs of switching to something better would be substantial, while the benefits would be marginal. So the parsec persists. This pattern appears throughout science. Consider how biologists classify organisms. The Linnaean taxonomy of kingdom, phylum, class, order, family, genus, species was developed in the 1700s. We now know it doesn't perfectly reflect evolutionary relationships. Modern cladistics provides better approaches. Yet Linnaean names persist because millions of species have been named using this system. Changing would require renaming countless organisms and rewriting countless references. Or consider how chemists name organic compounds. The UPAC naming system is logical and systematic, but many chemicals are still known by common names that reveal nothing about their structure. Acetone, formaldehyde, benzene. These names are historical accidents, but they persist because chemists know them and use them. Creating entirely new names based on chemical structure would be more logical but less practical. The same thing happened in physics with the CGS system, centimeters, grams, seconds, versus the MKS system, meters, kilograms, seconds. Both work perfectly well for calculations. The MKS system eventually became standard for most purposes because it aligns with SI units. But CGS persists in certain subfields like electromagnetism because generations of physicists learned it that way, and many classic papers use it. Converting everything would be possible but painful. These examples show a general principle. Scientific practice isn't determined purely by logic or efficiency. It's shaped by history, by the accumulated weight of past decisions, by the infrastructure built around those decisions. Once a practice becomes established, changing requires coordinating across many people and institutions simultaneously. That's hard. It requires agreement on what to change to, motivation to bear the transition costs, and mechanisms to coordinate the change. For measurement units, the difficulty is especially acute because units are foundational. They appear in every equation, every data table, every graph, every result. Changing a unit means potentially changing everything. That's why unit standardization efforts take decades and sometimes fail entirely. The United States still uses imperial units for everyday purposes despite repeated attempts to switch to metric. The infrastructure of road signs, product packaging, and public familiarity with feet and pounds creates enormous inertia. The parsec faces less resistance to change than imperial versus metric because it's used within a specialized scientific community, not by the general public. If astronomers collectively decided to switch to light years or some other unit, they could do it more easily than getting Americans to use kilometers. But they still haven't, because the benefits don't seem worth the costs. Here's what's fascinating about all this. The parsec isn't just a measurement unit. It's a window into how scientific communities actually function. Science is often portrayed as a purely rational enterprise, where the best ideas win based on evidence and logic. That's true in important ways. Bad theories that contradict evidence get rejected eventually. Good theories that explain observations gain acceptance. But science is also a social activity conducted by humans working in institutions with histories and cultures. Scientists use language and conventions that aren't purely determined by nature. They make choices about terminology, about notation, about units, about standards. These choices are partly rational based on practical considerations, but they're also partly arbitrary. based on historical accident and social coordination. The parsec exemplifies this perfectly. It's a rational choice in that it streamlines parallax-based distance calculations. It's an arbitrary choice in that 1 arcsecond has no cosmic significance. It's a social choice in that its persistence depends on coordinated community practice. All three factors matter. You can't understand why the parsec exists and persists by looking at only one of these factors. You need all three. This has implications for how we think about scientific knowledge. When we learn that Proxima Centauri is 1.3 parsecs away, we're learning a fact about the universe. The distance is real. Proxima Centauri genuinely is that far away. But we're also learning something about human choices. Someone decided to measure that distance using parallax. Someone decided to express the result in parsecs rather than light years or kilometers. Someone decided that was the appropriate unit for cataloguing stellar distances. The distance itself is a fact about nature. The unit we use to express it is a fact about human practice. Both are real. Both matter. Confusing them leads to misunderstandings about what science is and how it works. Some people hear that scientific units are arbitrary and conclude that science itself is arbitrary. That's wrong. The fact that we measure distance in parsecs rather than light years doesn't mean stellar distances are arbitrary. Proxima Centauri is closer than Sirius regardless of what units we use. The universe doesn't care about our measurement conventions, but our measurement conventions do affect how easy it is to do science, how naturally certain calculations flow, and how effectively we can communicate with each other. Other people insist that science must use the objectively best possible methods, and anything else is a failure. That's also wrong. Science is done by humans with finite time and resources. Using an measurement unit that's merely good enough rather than theoretically optimal is completely reasonable if switching would consume resources better spent on actual research. Perfect is the enemy of good. The parsec forces us to think more carefully about these issues. It's a reminder that science is both objective and constructed. Objective in that it discovers real facts about the universe. Constructed in that it does so using human-created tools, methods, languages, and conventions. Understanding this dual nature of scientific knowledge helps us become more sophisticated consumers of science. When we read that a galaxy is 50 megaparsecs away, we shouldn't just accept that as a pure fact delivered from on high. We should recognize it as a fact expressed in a particular framework using particular conventions. The distance is real, but the way we describe it reflects human choices. This perspective is valuable because it helps us understand scientific disagreements more accurately. Sometimes scientists disagree because the evidence is genuinely unclear. Different data sets point in different directions. Measurements have error bars that overlap. Theories make similar predictions that are hard to distinguish observationally. Those are legitimate scientific disputes about what nature is actually doing. But sometimes scientists disagree because they're using different conventions, different definitions, or different frameworks. They might actually agree about the underlying facts but express them differently. Or they might be answering subtly different questions without realizing it. These are disputes about human choices rather than about nature itself. They're still important disputes because conventions matter for communication and practice, but they're a different kind of disagreement. The parsec reminds us that both kinds of disagreement exist in science. There are disputes about facts and disputes about frameworks. Good science requires distinguishing between them. When astronomers debate whether a distant galaxy is 50 megaparsecs or 55 megaparsecs away, that's a factual dispute about measurement and uncertainty. When they debate whether to report distances in parsecs or light years, that's a framework dispute about convention and practice. Both matter, but they matter in different ways. Factual disputes get resolved by better observations and more refined theories. Framework disputes get resolved by community coordination and agreement on standards. Confusing the two leads to frustration and miscommunication. Now let's consider how modern astronomy has pushed the parsec to its limits. When Bessel first measured stellar parallax in 1838, he was working with nearby stars. The most distant star he could measure was maybe a few hundred parsecs away, and even that required extraordinary precision. For most of the 19th century, parallax measurements were limited to stars within about 100 parsecs of Earth. This made the parsec a perfectly sized unit. Most measured distances were between 1 and 100 parsecs. Those are human scale numbers. You can think about them intuitively. You can compare them easily. A star at 50 parsecs is clearly farther than a star at 25 parsecs. The unit served its purpose beautifully within its original domain. But as telescope technology improved and measurement techniques advanced, astronomers began measuring increasingly distant objects. By the early 20th century, they were studying objects thousands of parsecs away. By mid-century, millions of parsecs. By late century, billions of parsecs. The parsec had to scale up dramatically. This is where kiloparsecs, megaparsecs and gigaparsecs become essential. Without these scaled versions, we'd be talking about stars at 50,000 parsecs away, or galaxies at 50,000 parsecs away. Those numbers are unwieldy. Converting to kiloparsecs and megaparsecs keeps the numbers manageable. But here's an interesting question. As we push to larger and larger distance scales, does the parsec remain the best choice? For nearby stars, the parsec makes sense because it connects directly to parallax measurements. But for distant galaxies billions of parsecs away, we're not measuring parallax anymore. We're using completely different distance indicators, redshift and Hubble's law, standard candles like supernovae, the Tully-Fisher relation. None of these methods involve parallax directly. So why continue using parsecs at these scales? Largely for consistency and continuity. The distance ladder that connects nearby distance measurements to faraway ones works better if everything uses the same units. You measure nearby stars with parallax in parsecs. You calibrate Cepheid variables using those nearby stars. You use Cepheids to measure distances to nearby galaxies in megaparsecs. You use supernovae in those galaxies to measure even more distant galaxies in gigaparsecs. Every step builds on the previous step. Using consistent units throughout makes the chain of reasoning clearer. If we switched units at some distance scale, say using parsecs for nearby stars but light years for distant galaxies, we'd have to convert back and forth constantly. That introduces opportunities for errors. It makes the distance ladder harder to follow. Sticking with parsecs and its scaled versions throughout keeps everything in a unified framework. There's another consideration. Professional astronomy databases store enormous amounts of distance data. The Gaia satellite has measured parallaxes for over 1 billion stars. Galaxy catalogues contain millions of entries with distances. All of this data is stored in parsecs or kiloparsecs or megaparsecs. Converting all of it to different units would be a massive undertaking with no clear benefit. Imagine you're an astronomer who wants to analyse distance distributions for different types of galaxies. You query a database and get back thousands of distance measurements. If those measurements are all in megaparsecs, you can work with them immediately. If half are in megaparsecs and half are in millions of light years, you need to convert before doing any analysis. That's annoying and error-prone. Standardization has real value. This is why standards are so important in science and technology generally. Having everyone use the same units, the same file formats, the same communication protocols makes collaboration and data sharing vastly easier. The specific choice of standard matters less than the fact that everyone agrees on it. Parsecs aren't perfect, but they're standard. That's worth something. Modern cosmology provides an interesting case study. When measuring the largest scales in the universe, cosmologists often work with redshift rather than distance directly. Redshift measures how much light from distant objects has been stretched by cosmic expansion. It's directly observable and doesn't require assuming a particular cosmological model to convert to distance. Different cosmological models with different amounts of dark energy and dark matter and different expansion histories convert the same redshift to different distances. So cosmologists often report redshifts. and let people convert to distance using whatever model they prefer. This avoids baking model-dependent assumptions into the data. But when cosmologists do convert to distance, they typically use megaparsecs or gigaparsecs. Why not use light travel time directly, since redshift is fundamentally about light? Because distances in parsecs connect more naturally to other astronomical measurements. The size of galaxies is measured in kiloparsecs. The separation between galaxies and clusters is measured in megaparsecs. Using the same units for all these scales creates a coherent framework. There's also the issue of co-moving versus proper distance in an expanding universe. Because space itself expands, the distance to a faraway galaxy changes over time. Cosmologists distinguish between proper distance, how far away the galaxy is right now, and co-moving distance, which factors out the expansion. Both are typically expressed in megaparsecs or gigaparsecs because those are the established units. If cosmologists had decided to use light years or light travel time for these large-scale measurements, they could have. But parsecs were already standard in astronomy, and there was no compelling reason to switch, so parsecs and their scaled versions extended naturally into cosmology. This illustrates an important point about scientific fields: they don't exist in isolation. Cosmology grew out of astronomy. Cosmologists use many of the same tools, techniques, and data as other astronomers. Using the same units as the broader astronomical community facilitates communication and data sharing. Adopting different units would create barriers. The same pattern appears across science. Subfields use the units and conventions of their parent fields unless there's a strong reason to diverge. Planetary science uses astronomical units and parsecs because it emerged from astronomy. Astrobiology uses the same units because it combines astronomy and biology. Exoplanet researchers use the same conventions as stellar astronomers because they study stars that happen to have planets. This creates communities of practice with shared languages and standards. Within the community, communication is efficient because everyone speaks the same language. Between communities, translation may be necessary, but that's manageable because interactions are less frequent. The parsec thus serves not just as a measurement unit, but as a marker of community membership. If you naturally think in parsecs when discussing stellar distances, you're probably an astronomer or closely related field. If you naturally think in light years, you're probably coming from outside professional astronomy. Neither is wrong, but the different signals different backgrounds and training. This social function of technical language is often underappreciated. Jargon isn't just about precision or efficiency, it's also about establishing group identity and signaling expertise. When someone effortlessly uses specialized terminology correctly, it indicates they've been trained in that field. They know what they're talking about. They're part of the community. This can create barriers to entry for outsiders, which is both a cost and a benefit. The cost is that specialized language makes science less accessible to non-specialists. The benefit is that it allows efficient communication among specialists and helps identify who has relevant expertise. The parsec exemplifies this perfectly. It's technical enough that most people outside astronomy have never heard of it. That makes it poor for public communication, but it's standard enough that every professional astronomer knows it instantly. That makes it excellent for technical communication. Should we care about making science more accessible by using less specialized language? Yes, definitely. Public understanding of science matters for policy, education, and appreciation of human knowledge. Should we sacrifice efficient technical communication among experts to achieve that accessibility? No, that's counterproductive. Experts need to communicate efficiently with each other to make progress. The solution is code switching. Use technical language in technical contexts. Use accessible language in public contexts. Astronomers do this all the time. They write papers using parsecs and megaparsecs. They give public talks using light years. They translate between the two as needed. This is normal and appropriate. The parsec story reveals how measurement units carry more meaning than just numerical values. They encode history, reflect community practices, facilitate certain calculations, and signal expertise. Understanding this makes us more sophisticated about science itself. Consider what happens when you actually try to visualize a parsec. It's about 3.26 light years. Light travels at 300,000 kilometers per second. In 1 year, that's about 9.46 trillion kilometers. Multiply by 3.26 and you get roughly 31 trillion kilometers for 1 parsec. Try to picture that distance. You can't. Your brain isn't equipped to visualize distances at that scale. Even using familiar analogies doesn't help much. If you scaled down the solar system so Earth's orbit was the size of a coin, 1 parsec would still be over 100 kilometers away. That doesn't make it more comprehensible. It just replaces one incomprehensible scale with another. This is a fundamental challenge in astronomy. The distances involved are so enormous they exceed human intuition completely. We can calculate them. We can measure them. We can compare them to each other mathematically. But we can't really grasp them viscerally the way we grasp distances we experience in daily life. This is true whether we use parsecs or light years or kilometers. The parsec is no worse than alternatives in this regard. 1 trillion kilometers is just as incomprehensible as 3.26 light years is just as incomprehensible as 1 parsec. The universe operates at scales that our evolved intuitions weren't designed to handle. What we can do is develop a kind of mathematical intuition about these scales. We can learn that Proxima Centauri at 1.3 parsecs is close by stellar standards. We can learn that the galactic center at 8 kiloparsecs is a medium distance by galactic standards. We can learn that Andromeda at 780 kiloparsecs is close by intergalactic standards. These become reference points that help us orient ourselves conceptually even if we can't visualize the actual distances. Using consistent units helps build this mathematical intuition. When all nearby stars are measured in parsecs, all galactic distances in kiloparsecs, and all intergalactic distances in megaparsecs, you start to develop a sense of what those numbers mean in context. A star at 100 parsecs is fairly distant. A globular cluster at 10 kiloparsecs is in the outer halo. A galaxy at 50 megaparsecs is relatively nearby. These comparative judgments become second nature even though the absolute scales remain incomprehensible. This is another argument for maintaining the parsec despite its quirks. Switching units would disrupt this accumulated intuition. Astronomers who've spent careers working with parsecs have developed a feel for what different numbers mean. They don't need to consciously convert or calculate. They just know that 500 parsecs is a certain kind of distance in stellar terms. Changing units would force everyone to rebuild that intuition from scratch. There's a parallel here with temperature scales. Fahrenheit is clearly arbitrary and inferior to Celsius for scientific purposes. Water freezes at 32 degrees and boils at 212 degrees in Fahrenheit. Those are random numbers based on outdated calibration choices. Celsius puts freezing at 0 and boiling at 100, which is much more logical. Yet Americans continue using Fahrenheit for daily life because they've developed intuitions about it. They know 70 degrees is comfortable room temperature. They know 32 degrees means roads might be icy. They know 100 degrees is a very hot day. Switching to Celsius would work fine eventually, but it would require rebuilding all those intuitive reference points. The practical benefit doesn't seem worth the transition cost. The parsec is similar for astronomers. It's not optimally logical. But it works. They've built intuitions around it. Switching would mean relearning those intuitions. The benefit isn't obvious enough to motivate the change. There's also something to be said for historical continuity. When modern astronomers measure a stellar distance, they're participating in a tradition going back to Bessel in 1838. They're using the same conceptual framework, the same fundamental approach, refined and extended but still recognisably the same. That connection to history isn't just nostalgia. It's about maintaining continuity in how we understand and describe the universe. Scientific knowledge builds on itself. Current research depends on past research. Being able to compare modern measurements to historical ones requires using compatible units and methods. If we completely changed how we measure and report distances, we'd create a discontinuity that makes historical comparison harder. This doesn't mean we can never change anything. Science does update methods when benefits clearly outweigh costs. We no longer use the original definitions of the meter or kilogram. We've replaced them with more precise definitions based on fundamental constants. Those changes were worthwhile because they improved measurement precision significantly. But changing the parsec to light years wouldn't improve precision. It wouldn't enable new measurements. It wouldn't solve any technical problem. It would just be change for its own sake, or change to make things more intuitive for non-specialists. That's not a compelling enough reason when weighed against the disruption costs. Here's where we arrive at a deeper truth about the parsec and scientific practice generally. Science isn't just about discovering eternal truths that exist independent of human activity. Science is also about creating frameworks, standards, and practices that allow communities of researchers to work together effectively. Those frameworks aren't purely dictated by nature. They're shaped by human choices, historical accidents, and practical considerations. The parsec emerged from a specific historical context. Bessel needed to measure stellar distances using parallax. The parallax technique naturally produces angular measurements. Converting those angular measurements to distances required choosing a distance scale. The parsec was a convenient choice at that moment for those purposes. It stuck because it worked well enough and because changing would have been disruptive. That's not a story of discovering something fundamental about the universe. It's a story of humans making practical choices about how to organize knowledge and practice. Both aspects of science are real and important. The distances to stars are facts about nature. The units we use to express those distances are facts about human practice. Understanding this distinction helps us navigate science more intelligently. We can appreciate what's discovered versus what's constructed. We can recognize when debates are about nature versus about frameworks. We can be realistic about how science changes and why some changes happen quickly, while others take generations. The parsec will likely persist for the foreseeable future. It's too embedded in astronomical practice to change without massive disruption. Every astronomy student learns it. Every paper uses it. Every database stores it. That infrastructure creates enormous inertia. Unless some revolutionary new way of measuring cosmic distances emerges that works completely differently and provides dramatically better results, the parsec isn't going anywhere. And that's fine. The parsec isn't broken. It doesn't prevent progress. It works adequately for its purposes. Science can continue advancing while using measurement units that aren't perfectly optimal. Perfect is the enemy of good. The parsec is good enough. What makes the parsec story particularly illuminating is how it reveals the layered nature of scientific knowledge. At the surface level, we have measurements. Stars are at specific distances. Those are empirical facts we can verify through observation. Go deeper, and we have the methods used to make those measurements. Parallax observations, spectroscopic analysis, standard candles. These methods have their own assumptions and limitations. Go deeper still, and we have the frameworks used to express and organize those measurements. Units like parsecs, coordinate systems, distance scales. These frameworks are human constructions designed to make the measurements useful and communicable. They're not arbitrary in the sense of being random, but they're not dictated by nature either. They reflect choices made for practical reasons within specific historical contexts. All three layers are essential to science. You can't do astronomy without actual measurements of actual objects. You can't make those measurements without methods and techniques. And you can't make those measurements useful without frameworks to organize and express them. Each layer depends on the others. Understanding science requires understanding all three and how they interact. The parsec sits squarely in that third layer. It's not a measurement itself. It's not a technique for making measurements. It's a framework for expressing measurements in a form that astronomers find useful. That framework has properties that make it convenient for certain purposes. It also has historical origins that explain why it took the specific form it did rather than some alternative. This layered view helps clarify several things that often confuse people about science. First, it explains why science can be both objective and constructed simultaneously. The measurements are objective facts about the universe. The frameworks used to express those measurements are constructed by humans. Both statements are true and don't contradict each other. Second, it explains why scientific progress isn't just accumulating more facts. Progress also involves developing better methods, refining frameworks, and creating new ways to organize knowledge. Sometimes the big breakthroughs are conceptual rather than observational. Einstein's relativity didn't come from new observations initially. It came from reconceptualizing space and time. That's framework-level innovation. Third, it explains why scientists sometimes argue about things that seem like they should have clear answers. When the argument is about measurements, better observations can settle it. When the argument is about frameworks, it's more complicated. Different frameworks might organize the same facts differently without either being wrong. Choosing between them involves weighing practical considerations, not just checking observations. The Parsec exemplifies all of this. The distance to Alpha Centauri is a fact. The parallax measurement technique is a method. The Parsec is a framework. All three are necessary. All three play different roles. Confusion arises when we don't distinguish between them clearly. Now, let's consider what the future might hold for the Parsec. Will it still be the standard unit a century from now? Probably yes, though perhaps with some evolution. The infrastructure supporting it is so extensive that complete replacement seems unlikely. But modifications or supplements are possible. One scenario is that new distance measurement techniques could emerge that work so differently from parallax that parsecs become less natural. For example, gravitational wave astronomy is beginning to provide completely independent distance measurements to colliding black holes and neutron stars. These measurements don't involve parallax or any optical observation. They're based on the gravitational wave signal strength and characteristics. If gravitational wave distances become a major component of cosmic distance measurements, will astronomers still express them in parsecs? Probably, for consistency with other distance measurements. But they might also report them in different units more natural to gravitational wave observations. Perhaps units based on gravitational wave frequency or amplitude. This could lead to a situation where multiple distance units coexist for different purposes. Another possibility is that improved technology makes direct distance measurements so easy that the whole framework changes. Right now, measuring stellar distances is hard. It requires careful observations and sophisticated analysis. If future technology made distance measurements as easy as measuring brightness, the framework might shift. We might develop entirely new ways of cataloguing and thinking about cosmic distances. Consider an analogy from computing. Early computers required users to interact in machine code, directly manipulating bits and bytes. As technology improved, higher-level programming languages emerged. Eventually, graphical user interfaces made computing accessible without understanding underlying code at all. Each layer abstracted away complexity, changing how people thought about computing. Something similar could happen with distance measurements. Right now, we're still working fairly close to the observational level. We measure parallax or brightness and convert to distance using established relationships. Future astronomy might abstract that away. You might query a database for an object's distance and get a result without knowing or caring how it was measured. The unit might become less important at that point, but this is speculation. What we can say with confidence is that the parsec has shown remarkable staying power. It survived nearly 2 centuries of technological revolution in astronomy. Telescopes have gone from small refractors to space-based observatories. Detectors have gone from human eyes to sophisticated electronic sensors. Computational capabilities have increased by factors of billions. Through all of this, the parsec has persisted. That persistence suggests the parsec is meeting some fundamental need in astronomical practice. It's not just historical inertia, though that's part of it. The parsec genuinely works well for organising stellar and galactic distance measurements. It scales appropriately. It connects naturally to observational methods. It facilitates calculations that astronomers need to perform regularly. These pragmatic virtues ensure its continued use. There's also something elegant about the parsec that's worth appreciating. It's a unit defined by geometry, by the relationship between angles and distances. There's a purity to that. You observe an angle, you immediately know a distance. The connection is direct and unmediated. Compare this to more complicated distance indicators that require multiple steps of calibration and calculation. The parsec's directness is valuable. This geometric elegance is why the parsec works so well for the cosmic distance ladder. Each step in the ladder builds on previous steps, with parsecs providing a common language throughout. Parallax gives you distances in parsecs to nearby stars. Those nearby stars calibrate other methods. Those methods extend the distance scale further, all expressed in consistent units. The framework holds together coherently. Breaking that framework by switching units mid-ladder would be problematic. You'd introduce conversion factors at every step. Error analysis would become more complicated. The conceptual clarity would suffer. This is a strong practical argument for maintaining the parsec even if it's not ideal in isolation. Let's think about what an ideal distance unit might look like if we were designing one from scratch today, ignoring all historical constraints. What properties would we want? First, it should connect naturally to how we actually measure distances. Second, it should scale appropriately for different cosmic regimes. Third, it should facilitate calculations that astronomers perform regularly. Fourth, it should be comprehensible to non-specialists for communication purposes. The parsec scores well on the first three criteria. It connects to parallax measurements. It scales via kiloparsecs and megaparsecs. It facilitates brightness and luminosity calculations. Where it fails is comprehensibility to non-specialists. Light years do better on that criterion while being adequate but not ideal on the other three. An alternative approach would be to use natural units based on fundamental constants. In particle physics, it's common to work in units where the speed of light and Planck's constant both equal 1. This simplifies equations enormously because you don't need to carry around conversion factors. Everything is expressed in terms of energy or mass or length, using the same base units. Could we do something similar for astronomy? Define a distance unit based on fundamental constants rather than human measurement conventions? We could, but it's not obvious what that unit would be or why it would be better. The speed of light times 1 year gives you a light year, which is already in use. The Hubble length, the speed of light divided by the Hubble constant, is another natural unit. But it's about 14 billion light years, far too large for most purposes. The difficulty is that stellar and galactic distances don't correspond to any obvious fundamental scale in physics. They're set by astrophysical processes like star formation and galaxy evolution. Those processes involve complicated interactions between gravity, nuclear physics, and thermodynamics. They don't produce characteristic length scales that would serve as natural distance units. The parsec, for all its arbitrariness, is at least the right order of magnitude for nearby stellar distances. 1 parsec is a few light years. That's the typical separation between neighbouring stars in our galactic neighbourhood. It's not fundamental in any physical sense, but it's pragmatically appropriate. A unit based on fundamental constants might be physically more meaningful, but practically less useful. This illustrates a general tension in science between fundamental and pragmatic approaches. Physicists seeking unified theories want everything expressed in fundamental terms based on universal constants. Working scientists need units and frameworks optimized for the problems they actually solve. These goals don't always align. The result is often pragmatic compromises like the parsec. Consider another example from physics. The electron volt is a common energy unit in atomic and particle physics. It's defined as the energy gained by an electron accelerated through 1 volt of electric potential. That's completely arbitrary from a fundamental physics perspective. The size of an electron's charge and the volt are both historical accidents with no deep significance. Yet the electron volt is incredibly useful because it's roughly the scale of atomic and molecular energies. Chemical bonds have energies of a few electron volts. Atomic transitions involve electron volts. Nuclear reactions involve millions of electron volts. The unit matches the scales that atomic and particle physicists work with daily. That pragmatic fit trumps any concern about fundamental significance. The parsec is similar. It's not fundamental, but it fits the scale of stellar distances well. That pragmatic appropriateness matters more for working astronomers than any abstract consideration about what would be most fundamental. Science needs both fundamental understanding and practical tools. The parsec is a practical tool that works. There's one more aspect of the parsec worth exploring, its relationship to cosmic expansion. In a static universe, distance would be straightforward. Measure how far something is, and that's it. But we live in an expanding universe where space itself is stretching. This complicates what we mean by distance in deep, cosmological contexts. For nearby objects like stars in our galaxy, cosmic expansion is negligible. The gravitational binding of the Milky Way overwhelms any expansion effects. So when we say a star is 100 parsecs away, that's a straightforward statement. The distance isn't changing due to expansion on any relevant timescale. But for distant galaxies, expansion matters enormously. A galaxy 1 billion parsecs away is receding from us because space is expanding. The distance is increasing constantly. So what does it mean to say that galaxy is 1 billion parsecs away? Do we mean the distance now? The distance when the light we're seeing was emitted? The distance if we could freeze expansion and measure directly? Cosmologists distinguish between several different distance definitions. Proper distance is how far away something is right now, accounting for expansion. Co-moving distance factors out expansion, representing distance in a coordinate system that expands with space. Luminosity distance is defined by how bright an object appears. Angular diameter distance is defined by how large an object looks. In an expanding universe, these are all different. Which distance should we express in parsecs? Typically proper distance, or co-moving distance, depending on context. But this reveals that even defining what we mean by distance becomes complicated at cosmological scales. The parsec as a unit handles this fine. You can express any of these distance definitions in parsecs. But the conceptual framework around distance itself becomes more sophisticated. This is actually a beautiful example of how scientific understanding deepens. Early astronomers thought distance was simple. It's how far something is. Full stop. But as we learned more about the universe, we discovered that distance is more subtle. In an expanding universe, you need to specify what kind of distance you mean. That's not the parsec's fault. That's reality being more complex than we initially realized. The parsec adapts to this complexity. It remains a useful unit for expressing whatever distance definition you're working with. Proper distance in parsecs, co-moving distance in parsecs. The unit is flexible enough to accommodate refined understanding. That flexibility is part of why it has endured. Here's another interesting wrinkle. The parsec is defined by parallax, which requires Earth's orbital motion. But Earth's orbit isn't perfectly stable over very long timescales. Gravitational interactions with other planets cause subtle variations. Over millions of years, Earth's orbit will change slightly. Does this mean the parsec is changing over time? Technically yes, but pragmatically no. The modern definition of the parsec is fixed based on astronomical constants, as measured at a specific epoch. It doesn't track Earth's actual orbit anymore. It's been standardized and frozen. This is common for measurement units. They start based on some physical reference, then get formalized into fixed definitions that no longer depend on that reference. The meter started as a fraction of Earth's circumference, then became the distance between marks on a platinum bar, then became a multiple of a specific wavelength of light, and now is defined by fixing the speed of light and measuring time. Each redefinition made the standard more precise and more universal, moving away from the original physical reference. The parsec has undergone similar evolution. It started as literally the distance giving 1 arc-second parallax based on Earth's orbit. Now it's a defined constant equal to exactly 648,000 divided by pi astronomical units. That's a fixed number independent of what Earth's orbit actually does. The historical connection to parallax remains conceptually, but the practical definition is formalized. This formalization is important for precision science. If the parsec changed slightly as Earth's orbit evolved, that would create ambiguity in historical distance measurements. By fixing the definition, we ensure all measurements use consistent standards. That consistency enables comparing measurements across decades and centuries. It's another example of the dual nature we've been exploring. The parsec has historical origins in a measurement technique, but its modern form is a carefully defined standard that transcends those origins. Both aspects remain relevant. The historical context explains why the parsec exists and has its specific size. The modern formal definition ensures it works reliably for contemporary science. Understanding this evolution helps us appreciate how scientific standards develop. They often start from practical necessity in specific contexts. They get refined and formalized over time. Eventually they become infrastructure that enables further progress. The parsec has followed this pattern. It emerged from parallax measurements, became standardized across astronomy, and now serves as foundational infrastructure for cosmic distance scales. The broader lesson here extends beyond astronomy. Every scientific field develops its own specialized vocabulary, units, and frameworks. These aren't mere decoration or unnecessary complication. They're essential infrastructure that allows experts to communicate efficiently and think clearly about complex phenomena. Learning a field means learning its language, including its measurement systems. This is why introductory courses in any science spend significant time on units and definitions. It's not pedantry, it's foundational. You can't do chemistry without understanding moles and molarity. You can't do physics without understanding forces and energy. You can't do astronomy without understanding parsecs and magnitudes. These specialized concepts aren't obstacles to learning. They're tools that make learning possible. The parsec might seem like an obstacle at first. It's unfamiliar and non-intuitive. But once you understand it, it becomes a tool. It lets you think about stellar distances in a framework optimized for astronomical calculations. It connects you to the historical development of distance measurements. It signals membership in a community of practice. These are valuable functions beyond just expressing a number. This raises a question about science communication and education. Should we simplify specialized concepts to make them more accessible? Or should we teach people the actual framework scientists use, even if they're more complex? There's tension here. Simplification increases accessibility but loses fidelity. Accuracy maintains fidelity but reduces accessibility. The answer probably involves both approaches serving different purposes. For general public communication, light years work better than parsecs. They're more intuitive and adequate for conveying scales. For professional communication and education of future astronomers, parsecs are essential. They're what the field actually uses. What matters is being honest about this translation. When popularizers use light years instead of parsecs, they should acknowledge that conversion. When educators teach parsecs, they should explain why this less intuitive unit is standard. Transparency about frameworks and their purposes helps everyone understand what's happening. The parsec story has taken us on a journey through measurement, history, community practice, and the nature of scientific knowledge itself. We've seen how a seemingly simple thing, like a distance unit, reflects complex interactions between empirical facts, practical necessities, historical accidents, and social coordination. We've explored why science uses the tools it does and how those tools shape what science can accomplish. Every time you encounter a parsec in astronomical literature, you're seeing layers of accumulated history and practice. You're seeing Bessel's 1838 breakthrough. You're seeing the Babylonian choice to divide circles into 360 degrees. You're seeing generations of astronomers finding that parallax-based units streamline their work. You're seeing the inertia of established infrastructure resisting change. All of this compressed into a single measurement unit. This density of meaning is characteristic of mature sciences. The terminology and frameworks carry centuries of accumulated knowledge and practice. You can't fully understand a field without understanding where its tools came from and why they took their current form. The parsec is a perfect example. Its strangeness makes sense once you know its history. Its persistence makes sense once you understand its practical value and the coordination problems involved in changing. Think about how different this is from how science is often portrayed in popular culture. Science is frequently presented as a collection of facts to memorize. The speed of light is 300,000 kilometers per second. Stars are composed primarily of hydrogen and helium. The universe is 13.8 billion years old. These are indeed facts, but they're only part of the story. The deeper story involves how we know these facts, why we express them in particular ways, and what frameworks make them useful. The speed of light is measured in kilometers per second because those are convenient units for that particular measurement, though physicists often work in units where c equals 1. Stars are hydrogen and helium because that's what spectroscopy reveals, a technique developed over decades. The universe's age comes from multiple independent measurement methods that all converge on similar values. Each fact sits within a context of methods, frameworks, and historical development. Understanding that context is what separates superficial knowledge from genuine understanding. The parsec forces you to engage with that context. You can't really understand it without thinking about measurement techniques, unit conventions, and scientific practice. That's actually valuable pedagogically. It makes you think about how science works, not just what it has discovered. Here's another angle worth considering. The parsec's arbitrariness might actually be a feature rather than a bug in certain contexts. Because it's obviously a human construction based on measurement convenience, it reminds us that frameworks are constructed. That's a useful reminder. It prevents us from confusing our descriptions of nature with nature itself. Compare this to a hypothetical distance unit that seemed more natural or fundamental. We might be tempted to think of it as somehow more real, as if distances inherently come in those units. That would be a mistake. All distance units are human constructions for describing nature. Nature doesn't care what units we use. The distances exist independent of how we measure or describe them. The parsec's obvious artificiality keeps this clear. Nobody thinks parsecs are somehow cosmically fundamental. Everyone recognizes them as a practical tool astronomers developed. That transparency about human construction in science can be valuable. It helps maintain appropriate humility about the limitations of our knowledge and frameworks. This connects to deeper philosophical questions about the relationship between map and territory. Scientific theories and frameworks are maps of reality, not reality itself. The map is useful for navigating the territory, but it's not the same as the territory. Good maps are faithful representations, but they're still representations. They involve choices about what to include, what to emphasize, and how to organize information. The parsec is part of astronomy's map of cosmic distances. It's a choice about how to represent spatial relationships between celestial objects. That choice was made for good reasons and serves useful purposes, but it remains a choice, not an inevitability. We could have chosen differently. In fact, some contexts do choose differently by using light years instead. Understanding this map territory distinction helps prevent several common confusions about science. It explains why scientists can disagree about frameworks while agreeing about underlying facts. Different maps can represent the same territory faithfully, while organizing information differently. It explains why improving scientific understanding sometimes involves changing frameworks, rather than just adding facts. A better organized map reveals patterns that were obscure in previous organizations. It also explains why science can be culturally and historically situated, while still discovering objective truths. The frameworks and tools are culturally situated, shaped by particular historical developments, and practical needs. But the underlying facts being mapped are objective features of reality. Both things are true simultaneously without contradiction. The parsec exemplifies this perfectly. It's a historically and culturally situated choice made by a particular scientific community for practical reasons. It's also used to express objective facts about stellar distances that exist independent of human activity. The unit is constructed. The distances are discovered. Both statements are true and important. Now let's return to something we touched on earlier, but deserves deeper exploration. Why has the parsec not only survived but thrived despite being unintuitive to outsiders? Part of the answer involves what sociologists call community boundaries. Specialized language and concepts don't just enable communication within a community, they also mark boundaries around the community. They distinguish insiders from outsiders. This isn't necessarily intentional or malicious. It's a natural consequence of specialization. When a group of people work together intensively on specific problems, they develop shared language optimized for those problems. That language becomes second nature to group members while remaining opaque to outsiders. The opacity isn't the goal, but it's a side effect of optimization for insider communication. The parsec functions this way. For professional astronomers, it's the natural way to think about stellar distances. It's embedded in their calculations, their databases, their papers, their conversations. Using it signals membership in the professional astronomy community. Not using it, or being unfamiliar with it, signals outsider status. This can create barriers to entry, which is problematic for inclusivity and accessibility. But it also serves legitimate functions. It allows experts to communicate efficiently without constantly translating between specialized and common language. It helps identify who has relevant expertise when that matters. It creates shared culture that binds communities together. The challenge is balancing these considerations. We want science to be accessible and inclusive, but we also want scientific communities to function efficiently and maintain standards of expertise. Specialized language serves both goals to some extent while creating tension between them. There's no perfect solution, only trade-offs to manage thoughtfully. One approach is code switching, which we've mentioned before. Use specialized language in specialized contexts. Use accessible language in public contexts. Train people in both registers so they can move between them as needed. This requires extra effort but preserves both efficiency and accessibility where appropriate. Another approach is investing in translation and explanation. When specialized concepts matter for public understanding, explain them clearly rather than avoiding them. Help people understand why astronomers use parsecs and what that choice reflects about the field. This builds scientific literacy rather than just conveying isolated facts. The parsec can serve as a case study for these issues. It's specialized enough to mark insider status. It's important enough that understanding it matters for astronomical literacy. It's explainable enough that motivated outsiders can grasp it. Teaching people about the parsec becomes an opportunity to teach about how science develops frameworks, why those frameworks matter, and how they reflect community practices. This educational value is part of why the parsec strangeness is actually useful. If distance measurements used only intuitive units like light years, students might not think deeply about units and frameworks. They might treat them as transparent and inevitable, rather than as constructed tools with histories and purposes. The parsec's non-intuitiveness forces engagement with these meta-level questions. Consider how this plays out in practice. When astronomy students first encounter the parsec, they're confused. Why not just use light years? The instructor has to explain the historical origins, the connection to parallax measurements, and the practical advantages for calculations. In explaining this, the instructor is teaching not just a fact about units, but a lesson about how scientific practices develop and persist. That lesson generalizes beyond astronomy. It applies to understanding why chemistry uses moles, why physics uses natural units, why biology uses phylogenetic classification. Each field develops frameworks optimized for its particular needs. Those frameworks seem arbitrary to outsiders, but make sense once you understand the context. Learning to understand these contexts is part of becoming scientifically literate. The Parsec thus functions as a pedagogical tool, even beyond its practical utility for distance measurements. It teaches students to think about scientific practice, not just scientific facts. It reveals the human dimension of science, the choices and conventions that shape how we organize knowledge. These are valuable lessons that complement learning astronomical facts. Here's yet another dimension worth exploring. The parsec's definition, based on angular measurement, connects it to how we actually observe the universe. We don't measure stellar distances directly with meter sticks. We measure angles and brightness and spectra. Then we use theory and calibration to convert those observables into distances. The parsec acknowledges this reality by being defined in terms of what we can actually measure: angles. This is philosophically interesting. It suggests that our measurement units should reflect our actual observational access to nature, not just abstract ideals about what would be most fundamental. We observe angles, so we define distances in terms of angles. That's intellectually honest about our epistemic situation. Contrast this with defining a distance unit based on some physical constant we can't directly measure. That might seem more fundamental, but it would be disconnected from how we actually learn about cosmic distances. The parsec's connection to observation is a virtue, not a limitation. It keeps our theoretical frameworks grounded in empirical practice. This observational grounding has practical benefits too. When measurement techniques improve, units defined in terms of observables naturally incorporate those improvements. Better angular measurements automatically translate to better distance determinations in parsecs. The unit scales with our measurement capabilities rather than becoming increasingly disconnected from them. There's also something aesthetically pleasing about the parsec's geometric foundation. Distance defined by angle has an elegant simplicity. Draw a triangle, measure an angle, calculate the distance. The directness of this relationship has mathematical beauty. It's a pure geometric construction connecting angular and linear measures. This geometric purity contrasts with more convoluted distance indicators used at larger scales. Standard candles like Type Ia supernovae require understanding nuclear physics, stellar evolution, and explosion mechanisms. Tully-Fisher, relations connecting galaxy rotation speeds to luminosity, involve complex astrophysics. These methods work, but they're far from the geometric simplicity of parallax. The parsec preserves a connection to that geometric simplicity even when used for distances not measured by parallax. When we say a distant galaxy is 1 billion parsecs away, we're implicitly referencing that original geometric relationship. We're expressing distance in units that would produce a particular angular shift if we could somehow use parallax at those scales. That's conceptually clean, even if physically impossible. This matters for maintaining coherent theoretical frameworks. Physics thrives on geometric and mathematical elegance. When possible, we prefer formulations that reveal underlying simplicity and symmetry. The parsec's geometric definition fits this aesthetic. It's not just practical, but also intellectually satisfying for those who value mathematical structure. Of course, aesthetic considerations shouldn't override practical ones. If parsecs were beautiful but useless, they wouldn't have survived. The point is that they're both practical and aesthetically appealing to those trained in the field. That combination of utility and elegance strengthens their staying power. Let's think about one more angle. The parsec connects past and present in a tangible way. When modern astronomers use parsecs, they're speaking the same language as astronomers from a century ago. You can read papers from the 1920s about stellar distances and understand the measurements, because they are in parsecs. This continuity facilitates building on past work. Scientific fields with stable terminology and frameworks have advantages in terms of accumulated knowledge. You can integrate findings across decades or centuries more easily when the basic language remains consistent. Imagine if every generation redefined all the units and frameworks. Progress would slow dramatically because everyone would need to translate everything constantly. The parsec's persistence enables this kind of continuity. Bessel's original 1838 measurement of 61 cygni can be directly compared to modern measurements because both use parsecs. We can track how measurement precision has improved over 185 years while maintaining conceptual continuity. That's valuable for understanding the history and development of the field. This historical continuity has cultural value too. It connects current practitioners to the tradition they're part of. Knowing that you're using the same conceptual framework that Bessel pioneered creates a sense of participation in a long-term collective enterprise. That cultural connection matters for community identity and institutional memory. There's a delicate balance here. Too much continuity becomes stagnation. Fields need to evolve and adopt better methods when they become available. But too much disruption loses the benefits of accumulated knowledge and shared frameworks. The parsec has struck a successful balance by remaining stable enough to provide continuity, while being flexible enough to extend to new contexts. This flexibility deserves emphasis. The parsec hasn't remained static since 1838. It's been refined, formalised and extended. The original observational definition has been replaced by a precise mathematical definition. The unit has been extended to kiloparsecs, megaparsecs and gigaparsecs for different scales. It's been adapted to work with different distance definitions in expanding space. All of this evolution has happened while maintaining the core concept and maintaining compatibility with historical usage. That's exactly how scientific frameworks should evolve. Change what needs changing to accommodate new knowledge and capabilities. Preserve what's working to maintain continuity and coherence. The parsec's history demonstrates this balanced evolution in action. What can we learn from the parsec story that applies beyond astronomy? Several lessons emerge. First, scientific frameworks aren't purely logical constructions determined by nature. They're practical tools developed by communities to solve specific problems. Understanding where they came from and why they took their current form illuminates how science actually works. Second, established frameworks have inertia that resists change even when alternatives might be superior in some ways. This inertia comes from infrastructure investment, accumulated data, trained intuitions, and coordination costs. It's not irrational. It's a natural consequence of how communities function. Third, the distinction between what's discovered and what's constructed matters. Distances to stars are discovered facts about nature. Parsecs are a constructed framework for expressing those facts. Both are real and important, but they're real in different ways. Confusing them leads to misunderstanding science. Fourth, specialized language serves multiple functions beyond just technical communication. It marks community boundaries, facilitates efficient expert communication, carries historical meaning, and sometimes teaches meta-lessons about scientific practice. These multiple functions explain why specialized concepts persist despite seeming barriers to outsiders. Fifth, frameworks that connect to observation have virtues beyond pure theoretical elegance. Units defined in terms of what we can actually measure acknowledge our epistemic situation honestly. They ground abstract concepts in empirical practice. The parsec's connection to angular measurement exemplifies this. These lessons apply throughout science and beyond. Understanding them makes us more sophisticated consumers and practitioners of science. We can better appreciate why science uses the tools and frameworks it does. We can more accurately judge when frameworks should change and when stability is valuable. We can distinguish between disputes about facts and disputes about frameworks. The parsec thus serves as more than just a distance unit. It's a case study in how scientific practices develop, persist, and evolve. It's a window into the human dimensions of science that complement the empirical dimensions. It's a reminder that science is both discovery and construction, both objective and culturally situated, both timeless facts and historical practices. As utudikresletetig 1155 character, meg KB 8000 10,000 character kellernon. Folitetom. There's also something aesthetically pleasing about the parsec's geometric foundation. Distance defined by angle has an elegant simplicity. Draw a triangle, measure an angle, calculate the distance. The directness of this relationship has mathematical beauty. It's a pure geometric construction connecting angular and linear measures. This geometric purity contrasts with more convoluted distance indicators used at larger scales. Standard candles like Type Ia supernova require understanding nuclear physics, stellar evolution, and explosion mechanisms. Tully-Fisher relations connecting galaxy rotation speeds to luminosity involve complex astrophysics. These methods work, but they're far from the geometric simplicity of parallax. The parsec preserves a connection to that geometric simplicity, even when used for distances not measured by parallax. When we say a distant galaxy is 1 billion parsecs away, we're implicitly referencing that original geometric relationship. We're expressing distance in units that would produce a particular angular shift if we could somehow use parallax at those scales. That's conceptually clean, even if physically impossible. This matters for maintaining coherent theoretical frameworks. Physics thrives on geometric and mathematical elegance. When possible, we prefer formulations that reveal underlying simplicity and symmetry. The parsec's geometric definition fits this aesthetic. It's not just practical, but also intellectually satisfying for those who value mathematical structure. Of course, aesthetic considerations shouldn't override practical ones. If parsecs were beautiful but useless, they wouldn't have survived. The point is that they're both practical and aesthetically appealing to those trained in the field. That combination of utility and elegance strengthens their staying power. Let's think about one more angle. The parsec connects past and present in a tangible way. When modern astronomers use parsecs, they're speaking the same language as astronomers from a century ago. You can read papers from the 1920s about stellar distances and understand the measurements because they are in parsecs. This continuity facilitates building on past work. Scientific fields with stable terminology and frameworks have advantages in terms of accumulated knowledge. You can integrate findings across decades or centuries more easily when the basic language remains consistent. Imagine if every generation redefined all the units and frameworks. Progress would slow dramatically, because everyone would need to translate everything constantly. The parsec's persistence enables this kind of continuity. Bessel's original 1838 measurement of 61 Cygni can be directly compared to modern measurements, because both use parsecs. We can track how measurement precision has improved over 185 years, while maintaining conceptual continuity. That's valuable for understanding the history and development of the field. This historical continuity has cultural value too. It connects current practitioners to the tradition they're part of. Knowing that you're using the same conceptual framework that Bessel pioneered creates a sense of participation in a long-term collective enterprise. That cultural connection matters for community identity and institutional memory. There's a delicate balance here. Too much continuity becomes stagnation. Fields need to evolve and adopt better methods when they become available. But too much disruption loses the benefits of accumulated knowledge and shared frameworks. The parsec has struck a successful balance by remaining stable enough to provide continuity while being flexible enough to extend to new contexts. This flexibility deserves emphasis. The parsec hasn't remained static since 1838. It's been refined, formalized, and extended. The original observational definition has been replaced by a precise mathematical definition. The unit has been extended to kiloparsecs, megaparsecs, and gigaparsecs for different scales. It's been adapted to work with different distance definitions in expanding space. All of this evolution has happened while maintaining the core concept and maintaining compatibility with historical usage. That's exactly how scientific frameworks should evolve. Change what needs changing to accommodate new knowledge and capabilities. Preserve what's working to maintain continuity and coherence. The Parsec's history demonstrates this balanced evolution in action. What can we learn from the Parsec story that applies beyond astronomy? Several lessons emerge. First, scientific frameworks aren't purely logical constructions determined by nature. They're practical tools developed by communities to solve specific problems. Understanding where they came from and why they took their current form illuminates how science actually works. Second, established frameworks have inertia that resists change even when alternatives might be superior in some ways. This inertia comes from infrastructure investment, accumulated data, trained intuitions, and coordination costs. It's not irrational, it's a natural consequence of how communities function. Third, the distinction between what's discovered and what's constructed matters. Distances to stars are discovered facts about nature. Parsecs are a constructed framework for expressing those facts. Both are real and important, but they're real in different ways. Confusing them leads to misunderstanding science. Fourth, specialized language serves multiple functions beyond just technical communication. It marks community boundaries, facilitates efficient expert communication, carries historical meaning, and sometimes teaches meta-lessons about scientific practice. These multiple functions explain why specialized concepts persist despite seeming barriers to outsiders. Fifth, frameworks that connect to observation have virtues beyond pure theoretical elegance. Units defined in terms of what we can actually measure acknowledge our epistemic situation honestly. They ground abstract concepts in empirical practice. The Parsec's connection to angular measurement exemplifies this. These lessons apply throughout science and beyond. Understanding them makes us more sophisticated consumers and practitioners of science. We can better appreciate why science uses the tools and frameworks it does. We can more accurately judge when frameworks should change and when stability is valuable. We can distinguish between disputes about facts and disputes about frameworks. The Parsec thus serves as more than just a distance unit. It's a case study in how scientific practices develop, persist, and evolve. It's a window into the human dimensions of science that complement the empirical dimensions. It's a reminder that science is both discovery and construction, both objective and culturally situated, both timeless facts and historical practices. Counting addition to 5th section Bashkat Eoth, just esti a mem, there's also something aesthetically pleasing about the Parsec's geometric foundation. Distance defined by angle has an elegant simplicity. Draw a triangle, measure an angle, calculate the distance. The directness of this relationship has mathematical beauty. It's a pure geometric construction connecting angular and linear measures. This geometric purity contrasts with more convoluted distance indicators used at larger scales. Standard candles like type Weyr supernovae require understanding nuclear physics, stellar evolution, and explosion mechanisms. Tully-Fisher relations connecting galaxy rotation speeds to luminosity involve complex astrophysics. These methods work, but they're far from the geometric simplicity of parallax. The Parsec preserves a connection to that geometric simplicity even when used for distances not measured by parallax. When we say a distant galaxy is a billion parsecs away, we're implicitly referencing that original geometric relationship. We're expressing distance in units that would produce a particular angular shift if we could somehow use parallax at those scales. That's conceptually clean, even if physically impossible. This matters for maintaining coherent theoretical frameworks. Physics thrives on geometric and mathematical elegance. When possible, we prefer formulations that reveal underlying simplicity and symmetry. The parsec's geometric definition fits this aesthetic. It's not just practical, but also intellectually satisfying for those who value mathematical structure. Of course, aesthetic considerations shouldn't override practical ones. If parsecs were beautiful but useless, they wouldn't have survived. The point is that they're both practical and aesthetically appealing to those trained in the field. That combination of utility and elegance strengthens their staying power. Let's think about one more angle. The parsec connects past and present in a tangible way. When modern astronomers use parsecs, they're speaking the same language as astronomers from a century ago. You can read papers from the 1920s about stellar distances and understand the measurements because they're in parsecs. This continuity facilitates building on past work. Scientific fields with stable terminology and frameworks have advantages in terms of accumulated knowledge. You can integrate findings across decades or centuries more easily when the basic language remains consistent. Imagine if every generation redefined all the units and frameworks. Progress would slow dramatically because everyone would need to translate everything constantly. The parsec's persistence enables this kind of continuity. Bessel's original 1838 measurement of 61 Cygni can be directly compared to modern measurements because both use parsecs. We can track how measurement precision has improved over 185 years while maintaining conceptual continuity. That's valuable for understanding the history and development of the field. This historical continuity has cultural value too. It connects current practitioners to the tradition they're part of. Knowing that you're using the same conceptual framework that Bessel pioneered creates a sense of participation in a long-term collective enterprise. That cultural connection matters for community identity and institutional memory. There's a delicate balance here. Too much continuity becomes stagnation. Fields need to evolve and adopt better methods when they become available. But too much disruption loses the benefits of accumulated knowledge and shared frameworks. The parsec has struck a successful balance by remaining stable enough to provide continuity, while being flexible enough to extend to new contexts. This flexibility deserves emphasis. The parsec hasn't remained static since 1838. It's been refined, formalized, and extended. The original observational definition has been replaced by a precise mathematical definition. The unit has been extended to kiloparsecs, megaparsecs, and gigaparsecs for different scales. It's been adapted to work with different distance definitions in expanding space. All of this evolution has happened while maintaining the core concept and maintaining compatibility with historical usage. That's exactly how scientific frameworks should evolve. Change what needs changing to accommodate new knowledge and capabilities. Preserve what's working to maintain continuity and coherence. The parsec's history demonstrates this balanced evolution in action. What can we learn from the parsec story that applies beyond astronomy? Several lessons emerge. First, scientific frameworks aren't purely logical constructions determined by nature. They're practical tools developed by communities to solve specific problems. Understanding where they came from and why they took their current form illuminates how science actually works. Second, established frameworks have inertia that resists change even when alternatives might be superior in some ways. This inertia comes from infrastructure investment, accumulated data, trained intuitions, and coordination costs. It's not irrational, it's a natural consequence of how communities function. Third, the distinction between what's discovered and what's constructed matters. Distances to stars are discovered facts about nature. Parsecs are a constructed framework for expressing those facts. Both are real and important, but they're real in different ways. Confusing them leads to misunderstanding science. Fourth, specialized language serves multiple functions beyond just technical communication. It marks community boundaries, facilitates efficient expert communication, carries historical meaning, and sometimes teaches meta lessons about scientific practice. These multiple functions explain why specialized concepts persist despite seeming barriers to outsiders. fifth, frameworks that connect to observation have virtues beyond pure theoretical elegance. Units defined in terms of what we can actually measure acknowledge our epistemic situation honestly. They ground abstract concepts in empirical practice. The parsec's connection to angular measurement exemplifies this. These lessons apply throughout science and beyond. Understanding them makes us more sophisticated consumers and practitioners of science. We can better appreciate why science uses the tools and frameworks it does. We can more accurately judge when frameworks should change and when stability is valuable. We can distinguish between disputes about facts and disputes about frameworks. The parsec thus serves as more than just a distance unit. It's a case study in how scientific practices develop, persist, and evolve. It's a window into the human dimensions of science that complement the empirical dimensions. It's a reminder that science is both discovery and construction, both objective and culturally situated, both timeless facts and historical practices. EOF output 6919, total for 5th section Bash Eco 11550 plus 691 BC output 18474. Jo, as Utodek Reslet, måste 18474 karaktär. Meg Kebi 400 karaktär tadok hodza. When you look up at the night sky, those points of light are separated by distances we measure in parsecs. Proxima Centauri, our nearest stellar neighbour, sits 1.3 parsecs away. Sirius, the brightest star in the night sky, is 2.6 parsecs distant. Betelgeuse, that red giant in Orion, lies somewhere around 170 parsecs away, though uncertainty remains about its exact distance. The centre of our galaxy, home to a supermassive black hole, sits roughly 8,000 parsecs from us. These numbers tell stories. Stories of vast cosmic separation. Stories of light crossing incomprehensible distances. Stories of human ingenuity and measuring what seemed immeasurable for millennia. And stories of communities developing shared languages to describe their findings. The parsec is woven into all of these stories. It's how professional astronomers think about and discuss these distances. It's the framework that organises stellar and galactic cartography. It's the unit in which cosmic distance scales are calibrated. It's the language in which distance discoveries are communicated. Understanding the parsec means understanding more than just a unit conversion. It means understanding how measurement shapes knowledge, how communities coordinate around shared standards, how history influences present practice, how science balances pragmatic and theoretical considerations. These are profound insights that extend far beyond astronomy. So we arrive at the end of our exploration. We've traced the parsec from its origins in Bessel's 1838 parallax measurements through nearly 2 centuries of astronomical practice. We've examined why it emerged, how it persisted, and what it reveals about science as a human endeavour. The journey has taken us through geometry, history, sociology, philosophy, and back to the stars themselves. The parsec remains strange. It will always seem counterintuitive to those encountering it for the first time. That strangeness isn't a flaw. It's a feature that reflects authentic scientific practice. Science doesn't always use the most intuitive tools. It uses the tools that work best for the problems scientists actually solve, even when those tools seem peculiar to outsiders. This is worth emphasizing because scientific literacy requires understanding not just facts, but also practices. Knowing that Proxima Centauri is 1.3 parsecs away is less important than understanding what that number represents, how it was measured, why it's expressed in those particular units, and what frameworks make such measurements possible and useful. The parsec teaches all of these lessons. It forces engagement with measurement techniques, unit conventions, historical development, and community practices. It reveals science as something more complex and more human than the simple accumulation of facts. It shows science as an ongoing social enterprise with its own culture, language, and traditions. When professional astronomers use parsecs in their daily work, they're participating in that enterprise. They're using tools developed by previous generations, refined through collective experience, and standardized through community coordination. They're contributing to an accumulated body of knowledge that future generations will build upon. The parsec connects them to this larger endeavour. For those outside professional astronomy, understanding the parsec offers a window into how scientific communities actually function. It demystifies the specialised language without dismissing its importance. It explains why scientists make choices that might seem arbitrary or needlessly complex. It reveals the pragmatic considerations that shape scientific practice alongside the pursuit of truth. This understanding matters because science plays an increasingly central role in modern life. Policy decisions depend on scientific evidence. Technology development requires scientific knowledge. Public discourse invokes scientific authority. Being scientifically literate means understanding not just what science has discovered, but how science works, why it uses particular methods and frameworks, and what limitations and uncertainties remain. The parsec story contributes to that literacy. It shows that scientific frameworks are constructed by humans for practical purposes within historical contexts. It demonstrates how choices made for good reasons can become entrenched through network effects and infrastructure investment. It illustrates how specialised communities develop shared languages that facilitate insider communication while creating barriers for outsiders. These aren't criticisms of science, they're realistic descriptions of how science must function as a human activity carried out by communities working with finite resources and imperfect tools. Understanding this reality makes us better consumers of science, better evaluators of scientific claims, and better participants in science-informed discussions. Consider how this applies to current scientific debates. When experts disagree about climate models or pandemic responses or any contentious topic, understanding the role of frameworks helps interpret those disagreements. Sometimes scientists disagree about underlying facts because evidence is genuinely ambiguous. Sometimes they disagree about which frameworks, models, or assumptions to use while agreeing on basic facts. Distinguishing these types of disagreement matters enormously. Factual disagreements require better data and observation. Framework disagreements require careful comparison of different approaches and their trade-offs. Treating all disagreement as factual when some is actually about frameworks leads to confusion and frustration. The parsec provides a clear example where framework choice matters. Parsecs versus light years isn't about different facts. Both describe the same distances. It's about which framework better serves particular purposes. Professional calculation favours parsecs. Public communication favours light years. Both are legitimate choices for their contexts. Understanding this prevents false debates about which is correct. Imagine if every astronomy discussion devolved into arguments about parsecs versus light years. That would waste time and energy because both are valid frameworks. The real work of astronomy happens using either framework appropriately. Similarly, many scientific debates that seem intractable are actually framework disputes that could be resolved through clearer communication and recognition that different frameworks serve different purposes. This doesn't mean all frameworks are equally good. Some frameworks are demonstrably better than others for particular purposes. The parsec is better than parsecs for calculations involving parallax and luminosity. Light years are better for public communication. Recognizing these differences allows choosing appropriately rather than fighting over which is universally superior. The same principle applies broadly. Scientific frameworks should be evaluated based on how well they serve their intended purposes, not on abstract criteria of perfection. A framework that facilitates research, enables communication, and organises knowledge effectively is good enough, even if it's not theoretically optimal. This pragmatic view of scientific practice is liberating. It removes the pressure for science to be perfect in every detail. It acknowledges that science is done by humans working with whatever tools are available and good enough. It recognises that progress happens through incremental improvement rather than revolutionary perfection. The parsec has made incremental improvements over 185 years. The basic concept remains, but definitions have been refined, precision has increased, applications have extended to new scales and contexts. This gradual evolution is typical of successful scientific frameworks. They adapt and improve while maintaining enough continuity to preserve accumulated knowledge. Looking forward, the parsec will likely continue evolving. New measurement techniques like gravitational wave astronomy might introduce new considerations. Increasingly precise astrometry from space-based missions might refine the distance scale. Improved understanding of cosmic expansion might clarify distance definitions. Through all of this, the parsec framework will probably persist while adapting to new contexts. This persistence isn't guaranteed by any fundamental necessity. If some revolutionary new framework emerged that offered dramatic advantages, astronomy could eventually transition to it. But such transitions are difficult and rare. The parsec has proven robust enough to handle everything astronomy has thrown at it so far. Absent compelling reasons to change, it will likely remain standard. What would constitute a compelling reason? Perhaps a completely new way of measuring distances that makes parallax obsolete and naturally produces different units. Perhaps a unified framework that connects distance measurements across all scales more elegantly than the current distance ladder. Perhaps practical considerations like database design or international coordination that somehow favour different conventions. These scenarios seem unlikely but not impossible. Science does sometimes undergo paradigm shifts that restructure entire fields. If that happened to cosmic distance measurements, the parsec might finally be replaced. Until then, it remains the working framework that enables progress. There's something poetic about the parsec's survival against periodic challenges. Light years have always been more intuitive, metric units are more standard, natural units are more fundamental, yet the parsec endures because it works. It serves the practical needs of working astronomers better than alternatives. That pragmatic fitness ensures its continued use. This pragmatic fitness connects to deeper truths about how progress happens in any field. The best tools aren't always the most elegant or intuitive. They're the ones that work well enough, that integrate well with existing practices, that solve actual problems people face. Optimizing for theoretical perfection can miss these practical considerations. The parsec succeeded because it solved real problems for real astronomers doing real work. It converted parallax measurements to distances efficiently. It scaled well to different regimes. It facilitated calculations that astronomers performed regularly. These unglamorous practical virtues mattered more than theoretical elegance or intuitive appeal. This lesson applies beyond science. In any field, the tools and frameworks that succeed are those that serve practitioners' actual needs, not those that seem best in the abstract. Understanding what problems people are actually trying to solve reveals why they use the tools they do. Judging those tools requires understanding that context. The parsec's context is astronomical research carried out by communities of professionals using specific techniques to measure cosmic distances. Within that context, the parsec makes perfect sense. Outside that context, it seems bizarre. Both perspectives are valid. The key is recognizing which context you're in and adjusting expectations accordingly. When reading professional astronomy papers, expect parsecs. They're the native language of the field. When reading popular science articles, expect light years. They're better for general audiences. When teaching astronomy, students teach both and explain why each is used in different contexts. This prepares students to navigate between professional and public discourse. This code switching between specialized and general language is a crucial skill for scientists. They need to communicate precisely with colleagues using technical frameworks. They also need to communicate clearly with the public using accessible language. Both are important. Neither should completely replace the other. The parsec and light year exemplify this duality. Professional astronomers need parsecs for their work. The public needs light, years for understanding. Both units describe the same reality. They serve different communicative purposes. Managing this distinction successfully requires understanding both frameworks and translating between them appropriately. As we conclude this exploration, reflect on what the parsec represents. On one level, it's simply a distance unit defined as the distance at which one astronomical unit subtends an angle of 1 arcsecond. That's the technical definition, but on deeper levels, the parsec represents layers of meaning and significance. It represents the history of astronomy's quest to measure stellar distances, from ancient speculation through Bessel's breakthrough to modern precision astrometry. It represents the geometric elegance of parallax as a distance measurement technique. It represents the pragmatic choices made by scientific communities to facilitate their work. It represents the inertia of established practices and the coordination cost of changing them. It represents the distinction between what's discovered and what's constructed in science. It represents how frameworks organize knowledge without being determined by that knowledge. It represents the social dimensions of science that complement its empirical dimensions. It represents how history shapes present practice in ways that persist long after their original contexts have changed. All of this packed into a single measurement unit. That density of meaning is characteristic of mature scientific concepts. They're never just their technical definitions. They carry accumulated history, practice, and significance. Understanding them fully requires unpacking those layers. This unpacking reveals science as richer and more interesting than simple collections of facts. Science is an ongoing human endeavour with history, culture, and social structures. It discovers objective truths about nature, while using frameworks and tools that are human constructions. Both aspects are essential and inseparable. The parsec beautifully illustrates this dual nature. The distances it measures are objective facts about where stars and galaxies actually are in space. The parsec itself is a constructed framework that humans developed to express those distances conveniently. Both the facts and the framework are real. Understanding science requires understanding both and how they relate. We can now answer the question posed at the beginning. Why does astronomy use this strange unit that almost no star actually sits at? Because it emerged from the parallax measurement technique that first measured stellar distances. Because it proved convenient for astronomical calculations. Because it became standardized across the field. Because changing would disrupt extensive infrastructure. Because it works well enough that benefits of switching don't justify costs. These aren't separate reasons. They're interconnected aspects of how scientific practices develop and persist. The parsec exists and endures because of practical utility, historical accident, network effects, and accumulated infrastructure. All of these factors matter. None alone would be sufficient. Together they explain why this peculiar unit dominates professional astronomy. Thank you for joining this deep dive into the parsec. If you've gained new appreciation for how scientific practices work, how measurement frameworks develop, how communities coordinate around standards, then the time was well spent. The parsec is more than a distance unit. It's a window into science itself. The stars remain where they are, scattered across incomprehensible distances. Whether we measure those distances in parsecs, light years, kilometers, or any other unit, the cosmos doesn't care. But we care, because measurement is how we make sense of the universe. The tools we use to measure shape what we can discover and how we understand it. The parsec has been one of those tools for nearly 2 centuries. It likely will continue serving that role for the foreseeable future. Understanding it means understanding something fundamental about how science works, how knowledge accumulates, and how humans collectively make sense of reality. Look up at the night sky one more time. Those stars are separated by parsecs. Each parsec represents about 31 trillion kilometers, about 3.26 light years, about 206 and 265 astronomical units. Each parsec carries history from Babylon through Bessel to today. Each parsec enables calculations that reveal the universe's structure. Each parsec connects us to a community of astronomers past and present, working to understand the cosmos. That's what a parsec really is. Not just a number, but a story a story of measurement, discovery, practice, and persistence. A story of humans reaching beyond ourselves to comprehend distances we can't directly experience. A story of science as both objective investigation and social construction. The Parsec remains strange. That strangeness is honest. It reflects real scientific practice rather than sanitized ideals. Embracing that strangeness, understanding where it comes from and why it persists, makes us more sophisticated about science itself. That sophistication is valuable in a world increasingly shaped by scientific knowledge and technological capability. Keep looking up, keep asking questions, keep seeking to understand not just what we know, but how we know it. The cosmos rewards curiosity with endless wonders. The Parsec is one small part of that larger story of human curiosity reaching toward cosmic understanding. Good night,